right. Well, thank you very much, Susan, and thank all of you for joining us today. And many of you are repeats, and we certainly appreciate that as well. As Susan mentioned, today the subject today is in response to our audience requests. They're requesting more information on the changes they have seen coming along with the Firetube boiler design. Some of these cast and concrete principles in design are being compromised. And people are asking why, especially when the boiler, which has been around for so long and has such a tradition of both high efficiency and longevity, is not what it was even 5 years ago. So, what's going on? To answer that question, and in keeping with our policy of not making this a 45-minute commercial for Cleaver Brooks, I'm going to answer the question by telling you what we as an industry are being asked to accomplish, and then relate to you what general design areas all of us in this industry have to look at to arrive at the desired outcomes. Now, taking this a bit further and acknowledging all of us may take a different approach in addressing the specifics for design change, I'll show you what Cleaver Brooks has done to address the demands because, quite frankly, I'm not privy to what our competition did or didn't do, but I can say this for certain. We all tried to do the best that we possibly could and tried to do it without compromising efficiency and the longevity of the product while at the same time keeping the cost in line as well. And it's a pretty tall order for all of us. So with this in mind, what we will be covering today will start with just a brief synopsis of how boilers have evolved over the years before highlighting the specific market drivers which have dictated to our industry that pretty dramatic changes need to be made to this very popular boiler design. And then from here, I'll describe what general areas any manufacturer needs to focus on in order to assure the desired results. And then I'll show you some of the specific options within these areas which can be taken to affect the outcome before getting into Cleaver Brooks' final results. And then I'll conclude, as I normally do, with a final summation of what at least I think are the takeaways for today, and then we'll follow that up with the Q&A. So that's today's plan. And as stated, I thought it may be helpful to begin by giving you a brief review of how boilers have evolved over the years as they were called upon to satisfy and meet various applications and needs. For instance, here you see a boiler that was discovered in Egypt, and it goes way back to 5 or 6 BC, and was probably used to heat water to above 100 degrees centigrade or 212 degrees Fahrenheit. And this meant that it had to contain some pressure. And then on the right you see Hero's engine, which goes back to the 1st century BC, and it consists of a burner, a boiler, and steam drum. And the steam drum has turbojets, causing the drum to spin on its axis, or in other words, it's using the steam as a motive force as opposed to a heating medium. Here you see another form of hot water boiler found in Europe, which was solid fuel fired, and it goes back to about 80 AD. And again, this boiler was a pressure vessel, but it was limited in its rated temperature because of its bronze construction. Continuing on now to more modern times, we find an example of the type of boiler we will be discussing today, the Firetube boiler. And this time it's on wheels and fired with wood or coal. Now, these steam engines, or these behemoths, were massive in size and weighing up to 200,000 pounds, and they could reach speeds of about 100 miles per hour. Now, looking at the cross-section of the steam locomotive Firetube boiler, you find it has a furnace where the radiant energy is released, a single-pass convection zone consisting of fire tubes secured to the furnace and the front tube sheet. Now, as the water was heated, it turned to steam, and the steam was released to the steam dome, from which the steam was then delivered to the driving pistons, which were using the motive force to drive the wheels either forwards or backwards. Now, without these trains and the use of the motive force of steam, we would not have had the Industrial Revolution that we experienced beginning in the 1860s. as the Union Pacific and the Central Pacific Railroads connected their respective lines in 1869, and thereby providing a commercial connection in America which completely spanned the coast from east to west. And speaking of motive force, we now advance to the 20th century and find one of the most luxurious passenger ships ever made, the infamous Titanic, which so tragically sank during its maiden voyage on April 14, 1912, losing over 1,500 passengers to the icy waters of the Atlantic. You know, it weighed over 46,000 tons. It carried over 3,300 passengers. It was 60 feet from the water line to the boat deck. It had a draft of 34 feet and a length of over almost 900 feet. It was powered with 29 Firetube boilers. 24 of those 29 were double-ended, meaning they had 3 furnaces on either side of the boiler, total of 6. Then they had 5 single-ended boilers. So there was a total of 159 furnaces in these boilers, and they were fired with 825 tons of coal per day. Now, the 215-pound saturated steam for the boilers drove 2 4-cylinder engines and then 1 low-pressure steam turbine for the electrical power. Its speeds could reach 26 knots, which is about 30 miles per hour, and it was going about 25 when it hit the iceberg. I might also add at this point that boiler efficiency was not an important consideration, as the fuel being burned in those days, wood and coal, was plentiful and relatively inexpensive. As a matter of fact, in those early days, 1 boiler horsepower was denoted as 10 square feet of heating surface. And this was based on a standard using a coal-fired steam piston engine that required 30 pounds of water at approximately 100 degrees to reach 70 pounds saturated to generate 1 net shaft horsepower. So now, if you do the math, and I'll do that for you, and consider the overall efficiency, we deliver a total of 2,546 BTUs per hour of shaft power after receiving 33,475 BTUs of power source. Now, that's a rousing 8% fuel-to-steam efficiency. But again, that wasn't the concern at the time. It was only how much motive power can we get. Then in the mid-1940s, things began to change with the Firetube boiler designs. It was found through building Firetube boilers, often referred to as Scotch Marine boilers for the U.S. Navy during the war years, that boilers could be constructed using 2 to 3 square feet of heating surface to conserve physical size. And you know, quite frankly, the boilers performed all right. But the problem was they didn't last very long because of overheating. But for the Navy, the ships were, in their terms, short-term anyway. This all then led to the boiler industry getting together after the war and deciding on a standard for Firetube construction which would accommodate smaller size boilers but be more efficient and last at least 20 years or longer. And the outcome was standardizing on 5 square feet per boiler horsepower, examples as you see on the screen now, and evolving from the riveted construction on the left of the screen to an all-welded design as depicted with the boiler on the right. Now, this was also the time during which the boilers not only greatly improved with regard to efficiency and footprint, but the ability to burn various liquid and gaseous fuels also increased. So, with all of this as a bit of evolutionary background, let's take a look at what is driving the market today with regard to the Firetube boiler design. First of all, it again begins with improving energy efficiency. And though these Firetubes are already one of the most efficient designs out there, our customers want even more. This because fuel is such a large portion of a business's operating budget. And though gas prices have stabilized over the past few years, the growing worldwide demand is still keeping them up there and gradually rising, especially with the increasing fears of escalating carbon footprints and global warming. And then next we have the need for reduced footprint. Now, this is driven by ever-escalating construction costs and the need to reduce the square footage in those areas of the building which are considered non-revenue producing. And while we're at it, let's reduce the floor loading requirement as well. And then lastly, we have the need for emission reduction, which is primarily reducing nitrogen oxide emissions coming from the combustion process. And this because they are a precursor to low-level ozone or smog. Now, when looking at these market drivers and considering them from a manufacturer's design perspective, we have general areas of focus toward which we need to concentrate our attention. For instance, to reduce the weight, well, we need to look at reducing the number of passes in the boiler and the tube count. Knowing that this is going to reduce the amount of heat transfer surface, one of the things that we then need to seriously consider is we've got to improve the radiant heat transfer in the furnace, and at the same time, improve the amount of convective heat transfer in the tubes by increasing the heat transfer coefficient and the respective Reynolds numbers. And by the way, by concentrating on these areas, it not only impacts weight, but it also can reduce the physical size of the boiler as well. And because the furnace is enlarged to increase the radiant heating surface, this means we need less convective area or tubes to exchange heat. The other collateral benefit from a larger furnace is the heat release rate in BTUs per cubic foot of furnace volume, which has been reduced. And you know, this greatly helps to increase the overall life of the pressure vessel. So, what are we looking at in terms of weight and size reduction if we go about effecting design changes which increase the radiant area for heat exchange while reducing but improving the convective area? Well, as far as the weight reduction is concerned, and as you can see, we have the potential of reducing the weight by 30%. And the physical size of the boiler by 15% when comparing it to a similar capacity 4-pass Firetube boiler, which, by the way, really appeals to the architects designing new boiler rooms and facing ever-rising construction costs in addition to pressing demands to hold the budget. So far, I've made some general statements about how a design team goes about attacking the problem of reducing weight and footprint. In other words, the key engineering focus areas to accomplish the end result, but have said nothing about how it's specifically accomplished. Now, here on the screen, you see the furnace, again, where the radiant heat is transferred to the water surrounding it. It's the area of the greatest amount of heat transfer, mainly because of the significant temperature difference between the fire side and the water side. I mean, you're looking at over 2,000 degrees in the furnace in a substantially lower water side temperature. As a matter of fact, the furnace is at the power of 4 greater in temperature difference. Now, combining this significant difference with the mass flow and the turbulent velocity caused by the burner's combustion air fan, and if designed right, the furnace takes on a much larger role in converting heat energy to steam or hot water. So what then about the convective side of the heat transfer in a boiler? That heat which is transferred strictly by the hot gases and sees no radiant flame. Well, you know, in a Firetube boiler, these gases pass through a series of tubes and make several passes depending on the design. Now, this could be 2, 3, or 4 passes. The problem is, when the gases enter the various tubes at the outset, the velocity is the greatest and the turbulence is excellent in prompting excellent heat exchange. However, as the gases proceed, the velocity drops off, and as it does, a boundary layer forms coating the tube and impeding heat transfer. In other words, it's an insulator. And that's why additional tubes and passes are required to absorb as much heat as possible to increase the efficiency before these gases exit the stack. Now, what is the answer to all of this? Well, the answer is to break up that laminar flow with tubes that either have fins, dimples, or spirals, as you see on the screen now. This greatly enhances the Reynolds numbers, which is the ratio of inertia to viscous forces. In other words, you want to increase the inertia forces or turbulence, which in turn increases the heat transfer coefficient, or the amount of heat flowing across an area proportional to its delta T. Now, as you can see, by incorporating one of these design changes, you can expect the heat transfer to improve by as much as 85%, meaning less tubes and passes are required. Fact is, however, when a heat transfer engineer elects to go with one of these design changes, several factors have to be taken into account to optimize the outcome while trying to mitigate the required increase in combustion air fan horsepower, another energy user. That means he or she needs to address the number of dimples, the number of spirals or fins per inch, how they're oriented, and how big they are. This can really get tricky. And I'll talk to you a bit later about how the design engineers go about this today. So far, we've pretty well covered how a boiler can be reduced in size and weight from a design perspective. So now let's take a look at how we're going to address the market's needs with regard to efficiency and emissions. And to do that, we need to address enhancing combustion and control. Now, some of this I've already covered during other webinars in the past, but I wanted everyone to see how these areas are such an integral part of the overall solution in advancing the Firetube boiler design today. And we'll start with the combustor, or the burner. And without getting into any great detail of what goes into a high-efficiency and a low-emitting burner, just suffice to say it needs to be an excellent mixture of fuel and air, and then is able to stage the combustion so as to limit the amount of nitrogen oxides, which would be nitric oxide, NO, and nitrogen dioxide, NO2, while at the same time holding the CO, or carbon monoxide, to acceptable levels. Let's say no more than 50 parts per million. We'd like to keep it at 0 if we can. Now, this is no small order, especially when the burner is expected to modulate anywhere between, let's say, 6 to 10 turn down of the burner within that range. It's pretty difficult to accomplish all these things, but it can be done. And to accomplish the end result, it really requires more than just the burner by itself. It requires the high-efficiency, low-emitting burner to be properly engineered and then matched to the furnace in order to achieve the results. Remember, for a fuel to combust efficiently, it needs 3 things. It needs time, it needs temperature, and it needs turbulence. Now, the burner and its controls provide the temperature and the turbulence, but what provides us with the time to complete combustion? Well, it's the furnace. And that's why properly engineering the furnace and matching it to the burner is so important, because without that optimum match, the overall efficiency of the boiler will be significantly compromised. And next we have to have an optimized control system to achieve highest efficiency and the lower emissions. Now, on the screen now, you see a gun burner, which has been equipped with a single-point positioning combustion control system for controlling the fuel and the air mix. Now, note the system has a single jack shaft and a single drive motor, which is then driving linkages and cams to meter the fuel and air, and in this case, the flue gas recirculation, or FGR valve, for lowering NOx emissions. Now, we'll talk more about this in a minute as far as NOx emission reduction is concerned. Now, the problem with this system is if the burner modulates a lot because of a varying process or heating load, the ball joints, the rods, and the linkage arms, they tend to loosen, and they wear and they stretch, causing deflection and inaccurate and unrepeatable control of the mixture. This causes inefficiencies which often go undetected. So, to remedy the situation, the industry has come up with with a solution, and that's what we call parallel positioning system, which takes the place of the single shaft and the motor, along with its associated linkage, its arms, cams, and rods. replacing them, as you can see, with motorized actuators which independently control the fuel and air and the FGR if needed through a central electronic control device pictured here on the screen. This takes the variance out of the equation and delivers an efficient fuel-to-air mix time after time, regardless of the modulating frequency and extent. This saves energy by keeping us on the efficient side of the curve, if you will. Here, let me show you what I mean. Looking at this curve, the red arrows are directed to that point which is considered 100% combustion efficiency, or what we also refer to as stoichiometric combustion. Now, as we drift to the left of this point, you see the excess air is lessening as we are becoming fuel-rich, and the CO, carbon monoxide, is increasing as a result. Now, this is not only fuel inefficient, but it can be very dangerous as well. Now, if we go to the right of stoichiometric, you see the excess air increasing, and if we get beyond what is considered safe and very acceptable excess air at 15%, the efficiency continues to decrease. Again, I'll show you what I mean. Here you see a burner which was set up at 3% O2, which is the same as 15% excess air. And because of wear and hysteresis of the single-point positioning system, had drifted to the right of the curve and was operating at 7% O2. The result was a loss of 2% in efficiency, which is mentioned, often goes undetected unless someone is religiously monitoring excess air against a modulating load on a continual basis. And here's another thing which robs energy dollars but has nothing to do with the combustion control system. Boilers which spend an inordinate amount of time below the mid-firing range and their most efficient sweet spot, allowing the excess air to rise, losing significant amounts of energy.
Your session cannot.
They're losing significant amounts of energy through inefficient combustion, to say nothing about the high probability of cycling losses, which only adds additional fuel cost. Now, in this case, as far as the high excess air losses are concerned, a variable speed drive will certainly help reduce the amount of delivered air breaking through the air damper, elevating the O2 levels, but even this will not adequately solve the problem. Now, to solve the problem, the package boiler designer needs to engineer a burner which will repeatably hold excess air at 3% throughout its turn-down range, including mid to low fire. And this is difficult engineering, but it can and it has been done, and is one of the key reasons why the Firetube boiler is achieving the market's demands for higher operating efficiencies in a smaller and lighter package. Okay, this is all well and good, but what about emission reduction? Well, this is accomplished through the use of low-emission burners and incorporating flue gas recirculation. Remember, an uncontrolled natural gas burner will produce upwards of 120 parts per million of nitrogen oxide, which is admitted to the atmosphere. Now, these oxides, as I mentioned, are a precursor and a major contributor to ground-level ozone or smog. FGR is the process whereby a certain percentage of the flue gas is injected into the combustion air supply, reducing the flame temperature without quenching it. This temperature reduction can reduce thermal NOx production to less than 5 parts per million, and the technology has been proving itself for years as not only being very effective in controlling NOx, but cost-effective as well. So, that essentially covers the design areas which need to be addressed to achieve the market's demands for higher efficiency and lower emissions in a smaller, lighter, and yet robust package. But what we often get questioned on today in this era of instant gratification is, do boiler designers still go about development as they have in the past, with designs on paper, then prototype manufacture, then modifications, or scrapping it and starting all over? Well, you know, when I started in this business back in 1964, that's exactly what was done. And believe me, a lot of time and money was wasted. Today, however, things are dramatically different. Today, design engineers are using computational fluid dynamics and finite element analysis to not only design the boiler packages, including optimal radiant and convective heat transfer outcomes, but also the proper burner characteristics matched to the furnace to maximize efficiency and long asset life. These designs are then affirmed through the use of a complex algebraic formula applied electronically using finite element analysis. The process also includes a thorough analysis of the structural implications when one is applying the amount of heat transferred in the boiler along with the dramatic swings in delta T's, which are involving varying circulation rates and associated heat fluxes. For instance, analyzing the furnace and its stresses, because this is the area receiving the greatest amount of heat and very huge delta T's. What should the thickness of the furnace plate be? And should it be corrugated to lessen the weight, yet adding sufficient strength? And then there's the question of tensile strength and metal deformation caused by the various heat and pressure stresses that are being incurred. Here the engineers are looking not only at the furnace, but the tube sheets, including the ligaments and the tube attachments. Should they be rolled and flared? Should they be rolled and beaded? Should they be rolled, beaded, and welded? And when everything is finally designed and reaffirmed using the computational fluid dynamics and finite element analysis tools, the prototypes are constructed and the actual live results are tested and then confirmed. Now, this takes a fraction of the time the old empirical testing used to take, as much of the work was accomplished using the advances of the latest computer technologies. So now, turning specifically to Cleaver-Brooks, because as I mentioned at the outset, I really don't have the specifics on our worthy competitors' outcomes. The end result consisted, as far as we were concerned, with two basic models. One using the integral burner, which you see here and named the CBEX Elite, and the other using a gun burner and named the CBEX Premium, which I'll show you next. The CBEX Elite's feature set is shown on the screen, but what is really important to note is its NOx reduction down to less than 9 parts per million on the 100 through 2200 horsepower and 5 parts per million on the 500 through 680 horsepower, all while holding excess air at 5%. Now, other notables are its standard use of parallel positioning combustion control, its ability to hold 3% O2 throughout the entire modulating range with 30 parts per million NOx reduction, and then its peak efficiency at 85%. The CBEX Premium is similar in some respects to the CBEX Elite, but does not achieve as low a NOx reduction. It uses single-point positioning on the 100 through 800 horsepower range, does not have quite the turn down the Elite achieves, plus it has higher O2s, and overall, a lower yet what is considered in the industry to be an acceptable efficiency. So, some might ask, why the two different designs? Why two different models? Well, the answer is, besides the market calling for a smaller, lighter package to deliver high efficiency and lower emissions, they also want a price which delivers a price value suitable for specific needs. You know, maybe I don't need an ultra-low NOx level in my area. Or maybe my boiler has a steady load and doesn't modulate very much, so why am I paying for parallel positioning? And maybe technicians are more familiar with a gun burner. At least in my case they are. So why pay for something that I don't need or want? In these cases, the choice would most likely be the CBEX Premium type, which also reduces size and weight compared to the standard Firetube boiler. Because similar to the Elite, the furnace has been optimized, the corresponding gun burner has been engineered to match it, and it's a two-pass design including the optimized convection tubes. This also means the radiant area, the furnace, is absorbing the majority of the heat from the burner, and because the heat release has been reduced per volumetric area, the longevity of the pressure vessel has not been compromised, nor has the tube sheets, ligaments, or the tube attachments. In both the Elite and the premium packages, the optimized tubes are actually spiraled tubes, and as mentioned earlier, are used to increase convective heat transfer. By this I mean the tubes are specially designed to include a particular number of ribs per inch. The ribs are also machined at a specific angle with a specific height and width to provide the maximum contact area, while breaking up the laminar flow of the gases as they travel through the second pass before exiting the stack. And then, of course, the proper combustion control system was employed, giving the customer a choice depending on his or her needs and the value that they were looking for. The parallel positioning system, standard with the Elite, certainly has efficiency benefits, but if the boiler load is not varying, the cost-value benefit quickly fades. So, in the final analysis, a few of us in the industry accomplished the wishes of the market, in addition to offering a price-value relationship along with extended asset life. And though we did this in different ways, the results are similar, leaving the final decision up to the specifying engineer and the ultimate owner, who will be evaluating the various competitive differences, weighing them against not only the feature set and guarantees of the various manufacturers, but also who is delivering the best overall cost-value relationship for the long term. So, with that, here is at least what I consider the takeaways for today. Firetube boilers have been evolving for years based on various customer needs. The heating surface and gas passes can be reduced if provisions are made for increasing radiant and convective heat transfer, their coefficients, and the Reynolds numbers associated with staying. Extended surfaces in the tubes break up the laminar flow, increasing the heat transfer. Reducing thermal NOx is a time-temperature relationship. Imperative the burner and the furnace be matched to optimize results, especially important if you're retrofitting a new burner to an existing boiler. Make sure the application engineer, the sales engineers are taking this into consideration, properly matching that burner to the furnace. It makes a lot of difference. A 2% increase in O2 equals a 1% loss in efficiency. Most burners lose efficiency at mid to low fire. The sweet spot of a Firetube boiler could be maybe 80–90% of its total capacity. You got to know where that is, and then you want to try to make sure that boiler is sized to be at that particular rate most of the time. And when selecting a boiler, check the efficiencies at all firing rates, because they vary as you go from, in many standard boilers out there today, as you go from low to high fire is going to be less efficient than high fire. The sweet spot might be 90%, but there are products out there today which can hold that 3% throughout the entire firing range. So check into that. And with that, let's open up the wires, or open up the wire for some questions.